Yes, okay. So I asked you to find, so question 1, what are the limits, ranges of the following sets of data for the data below? So we have just the sample number. This is just our index number, 1 through 16. There's just 16 samples. And here we have the actual data values in grams. So we have to find these ranges of the middle 50% of data, which remember we talked about. The lower range is quartile 1. The upper limit of that is quartile 3. To find 68%, the middle 60% of data, remember if we have that normal distribution curve, is the mean plus or minus 1 standard deviation. So that's what is calculated here. It's minus 1 standard deviation, and here we have plus 1 standard deviation. And then to find 95%, it's plus or minus 2 standard deviations. So we've got minus 2 standard deviations for the lower limit and plus 2 standard deviations for the upper limit of that 95% range. And then I asked you, why do we often use standard deviation to describe the spread of data instead of variance? Well, that's because standard deviation is in the same units as the original data set. So we have grams here. Compared to variance, which would be grams squared and is harder to really like understand what that means. It's just a lot less intuitive. So that's why. So that was question 1. For question 2, let's say in a population of 18% of in a population, 18% of people have blood type A and 41% have blood type B. A couple people were asking me about blood types and stuff like that, and this is definitely this is something you should remember from like intro bio classes, but you can have, there are 4 blood types pretty much. There's A, B, AB, and O. So the question is, if a couple is randomly chosen, what is the probability they're neither A nor B? And I also gave you this table to fill out. So because the probability of being A or B, like actually blood types, being one or the other doesn't affect the others, they're independent. So you just find the probability of A and B by multiplying the probability of B times the probability of A. You can do that for the rest of the table or use the complement rules or the additive properties of probability to solve the rest of the table. But when we calculate the probability of being, let's see, neither A nor B, we actually get 0.234, not this value right here. And that's because we're, is that right? Oh, a couple, that's why. So it's this value squared because we're considering 2 people, right? So it's the probability of one person being neither A nor B, or it's blood type O would be another way to say that, times the probability of a second person also being type O. So we get this probability of not A and not B times itself, so squared. So the probability of a single person being neither A nor B is, yeah, that's what I just went over. If one partner is type A, what is the probability the second partner is also type A? So this is set up as a conditional probability. So given person A is type, or person 1 is type A, what's the probability person 2 is also type A? However, because A and B are independent events, when we use the equation for it, which is the probability of A and B divided by the probability of B, the probability of B cancels out. So we end up just with the original probability that we're asking for, which is the probability of being blood type A. Because A and B, or the probability of event A and event B, are independent events. For number 3, we're saying a statistician wants to branch into book writing, but wants to know the probability the book will sell to each demographic. They make a survey and ask people they ask 100 people, from different demographics whether or not they'd purchase the book. Of the people surveyed, 64 were adults, 71 said yes, and 8 of the teens said no. So because we're talking about 100 people, and those were the numbers of people from each of those demographics or groups, those are percents, right? So it's really just 0.64 or 64% of the people surveyed were adults. So that goes here. The probability of an adult essentially out of that group is 0.64. 71 said yes. So we really have 71% of people saying yes. And 8% of the teens, or 8% of people, were teens who said no. So that goes here. From there, this is pretty much just set up like the ducks with botulism and symptoms question from last week that we did in class. It's just an example of when 2 traits are dependent, so you can't use the multiplicative rule of probability to fill in the table. That was like the big takeaway from this. So assuming the sample is representative of the population, what is the probability a randomly selected teenager will purchase the book? Probability a person will purchase the book given that they're a teenager. So I reworded that for you so that it was a little easier to recognize that that's a conditional probability question. So I wrote that out as the probability of yes, given that they're a teenager, is equal to the probability of yes and teenager divided by the probability of being a teenager, which we get here. So yes and teen divided by the total probability of being a teenager. So the probability a selected teenager will purchase the book is 0.778. And then I asked you to make a figure for the data with all necessary elements. And this, I didn't include a title, but so we have the probability of an age group, or yeah, pretty much the probability that people from different groups will or will not buy the book. You could also have done a stacked bar chart. That would have been fine too, with age group on the x-axis. So looking at this, we see both teens and adults are likely to purchase this book. So there's not really a difference in being a teen or adult. It's that adults in general are more likely to buy the book compared to teens, but they're both pretty likely. And that's the homework. Were there any questions about the homework? Or any specific things you want me to explain a little bit more?
Yeah, I have a question for number 3.
Okay.
So at first I did the same exact thing. I divided the yes by the total amount of teens, but then I read your like explanation in the parentheses, and I was assuming that what is the percentage of yes teens throughout the whole population?
Okay. So I can see that. But yeah, it's really this like given
Okay.
that's really key, because it's telling you that you already have one piece of information, and then you're asking for the probability of something because of that piece of information. Does that make sense?
Yeah. Okay. I think it's just the wording.
I know probability problems are tricky in general, and making them wording them in a way that is really clear is difficult to make sure that everybody interprets them the same way. On the quiz and tests and stuff like that, I'll probably be bolding or like italicizing or underlining like keywords that I really want you to pay attention to. So just know that in the future, I'll be like underlining these.
Okay. Thank you.
Yeah, you're welcome. Are there any other questions? Oh, and as far as grading goes, I'll probably do like half credit or something like that, instead of like completely, marking it wrong, because I understand how difficult it is sometimes to understand the way that things are worded. But okay. If there aren't any other questions, then we'll just start with
I had a question.
Okay.
For the table on this same question number 3, I didn't put the decimals. I just put like whole numbers. Is that all right, or should it always be decimals?
It should always be decimals. And also,
Okay.
Using whole numbers isn't a probability or a proportion. And that's why.
Okay, thank you.
Yeah, you're welcome. Okay. Okay, so I will start with the lecture. Okay. Okay, so this week I guess we'll do the warm up first, sorry. So you're a botanist studying the role of native pollinators and the effect of pesticides in Southern California coastal habitats. So we'll go ahead and do the warm up really quick. Okay, so native bees pollinate a coastal habitat consisting of 14% mustard, 21% poppy, 23% sunflower, and 42% radish. And I asked, what's the probability of a bee landing on a poppy and then a sunflower? So one and then the other. A good way to start is to make like a little table of this data so that you can use it for the rest of the calculations. Cool. Okay, so the probability of between two independent events for one and then the other to happen is just the probability of event A times the probability of event B. So this is just the probability of poppy times the probability of sunflower. For B, we have a bee lands on one flower, then another. What's the probability it landed on a radish or a mustard, but not both? So we get, this is equal to the probability of, well, this one's actually a little bit trickier because if we think about it, right, we have two trials, and in those two trials, a couple things can happen. You could land on a radish twice. You could land on a mustard twice. You can land on a radish and then a mustard, or a mustard and then a radish. So the probability that we're looking for are these two. Either it landed on a radish 2 times or it landed on a mustard 2 times, but it did not land on a mix of the two. So the probability is this plus this, which will be equal to radish times radish and mustard times mustard. And those two added together. For C, we have a coastal restoration project that begins weeding of invasive plants in the area, and mustard is completely eradicated. What's the probability a bee lands on a poppy? So this one's a little bit trickier. The best way to go about thinking about this is really thinking about what the word percent means. So percent means of 100 or per 100. So for problems like this, it's best to think of these percentages as numbers out of 100, like whole numbers out of 100. So that would mean that there are 14 mustards, 21 poppies, 23 sunflower, and 42 radishes. In the original population of flowers, right? But then we completely get rid of mustard. And so these are the remaining flowers that we have. Now we don't have out of per 100 anymore. We have per out of the total here. So now I'm calculating the new sum total. So imagining this field of 100 flowers, 14 of which were mustard, those are all pulled out. That means there are only 86 flowers left in this field. So now we have to calculate new proportions, like what proportion of these 86 flowers are each of these. So for poppy, we have 21 out of 86 flowers are poppies. 23 out of 86 are sunflowers, and 42 out of 86 are radishes. Therefore, the probability of a bee landing on a poppy is just this. For number 2, this one is again pretty much the same thing as the ducks and botulism problem. So I give you a couple of probabilities to fill into the table. So we have the probability of a bee coming into contact with insecticide. So that's what I represented as C, just contact. The probability that a bee shows paralysis, so the probability of paralysis is 0.42. And the probability of neither coming into contact with insecticide nor showing signs of paralysis is 0.53. So those are the numbers that you can fill in with what I've given you. So if the probability of coming into contact is 0.36, the probability of not coming into contact is 1 minus that, the complement of that. We can do the same thing here for paralysis. So 1 minus the probability of paralysis, the probability of not having paralysis. And we see immediately that we can't use the multiplicative rule of probability. Therefore, these are not independent. So no, the traits are not independent because the probability of whichever ones really, we can say not P and not C does not equal the probability of not P times the probability of not C. A randomly selected bee does not show signs of paralysis. What is the probability as come to contact with insecticide? So first, let me finish filling out this table. So if the probability of not P, not paralysis, is 0.58, and 0.53 of that is already here. The remaining probability goes here. It's the difference between the two. Same here, we can fill these out going upwards. So if the total probability of coming into contact with insecticide is 0.36 and 0.05 of that is here, then the remaining has to be up here. And same for this one. So when traits are not independent, you need to use addition and subtraction to fill in these tables instead of multiplication. So a randomly selected bee does not show signs of paralysis. So what is the probability it has come into contact with the insecticide? This is again worded as a conditional probability, as a conditional probability problem. So the probability of that it has come into contact given that it does not have paralysis equal to the probability of C and not P divided by the probability of not P equal to, so C and not P divided by the total probability of not being paralyzed. What's the probability of a bee becoming paralyzed after being exposed to insecticide? So this is another conditional probability question. So we already know that the bee has been exposed to insecticide. It has come into contact with insecticide. Therefore, what's the probability that it will become paralyzed? So the probability of paralysis given it's already come into contact is equal to the probability of paralysis and contact divided by the probability of contact. Oops. So probability of P and C divided by the probability, total probability of coming into contact is 0.86. And if we think about that, that actually makes sense, right? If a bee comes into contact with insecticide, right, we expect it'll probably be paralyzed or have paralysis. Same for here, right? If we say that a bee does not show any signs of paralysis, there's a low chance, a 0.8 chance or an 8% chance that it has come into contact with the insecticide. So yeah, this week we're doing binomial and Poisson distribution, but first we'll start with binomial. So this is another probability distribution. Last week we were talking about rolling a die, which would be a uniform distribution, right? We have a uniform chance of any one number appearing, 1/6 if we're doing a 6-sided die. A binomial distribution is a little bit different, and it's essentially a discrete version of a normal distribution. The distribution of the expected number of successes out of a specific number of K trials is how this is set up, where each trial has only one of two possible outcomes. And these are called Bernoulli sampling experiments. And yeah, it's essentially a discrete version of a normal distribution where, oh, sorry, I'm trying to see. There we go. Okay. With a normal distribution, you'd have something like this. Whereas with a binomial distribution, because it's discrete, it's more like this, where each bar represents the probability of a certain event occurring. or the number of times that event occurs. So when we have a binomial distribution, there are two possible outcomes, P and Q, where P is the probability of a success and Q is the probability of a failure, which means that it's equal to 1 minus P, right? P plus Q equals 1 because the probability of a success or a failure equals 100%, right? Either a success or a failure has to happen. There are 4 assumptions of a binomial distribution. The first is that there are only 2 possible outcomes, a success or a failure. And we arbitrarily determine what those are, right? A success or a failure could be male or female, or heads or tails. And it doesn't matter which one out of those we decide is a success or a failure. It's arbitrary, and we'll get into that a little bit more. There are K trials, so a set number of trials per sampling unit. The third assumption is that the probability of success is constant for all trials. And the fourth is that each trial is independent. These first two are pretty easy to figure out right at the beginning, and these are a little bit more difficult. They take a little bit more figuring out. So a good example is a fair coin flip. And again, we arbitrarily decide whether heads or tails is a failure. In this case, we're going to say heads is a success. We want to get heads, and tails is a failure. So the probability of flipping 2 heads or getting 2 successes is P times P, which is equal to P squared. So 0.5 times 0.5, 0.25. The probability of flipping 2 tails or getting 2 failures is Q times Q. So a tail times a tail, again, 0.5 times 0.5, 0.25. However, we can also flip 1 head and 1 tail in 2 orders, head and then tail, and tail then head. So the probability of flipping 1 head and 1 tail is this. So P squared plus P squared, or PQ, sorry, PQ plus PQ is equal to 2PQ, so 0.5. And this is really more like PQ plus QP, if we're thinking about it technically, but it doesn't really matter mathematically. And this is kind of what I was referring to also in the warm-up today. Since the only possible outcomes for 2 coin flips are 2 heads, which would be P squared, 2 successes, heads, tail, or tails and then heads, so 2PQ, and 2 tails or Q squared, 2 failures. The probability of 2 heads plus the probability of a head or a tail or a head, plus the probability of 2 tails is equal to 1. Those are all possible outcomes in 2 trials of 2 coin flips. And that's shown here as well. Right, so you can get 2 heads, a head and then a tail and then a head, or 2 tails. So this is the entire sampling space and all possibilities. As an equation for binomial distribution, this is what it looks like, where we have this P of R, the probability of the number of successes is equal to this KP term, which really just breaks down into this factorial fraction. We have K factorial divided by R factorial divided by the difference between K minus R, which is just the number of failures, K minus R. So the total number of trials divided minus the number of successes gives us the number of failures. And that's multiplied by the rest of this term up here. We have the probability of success raised to the number of successes times 1 minus P. So the probability of failure raised to the number of failures. So R is the number of successes, K is the number of trials. Once again, P is the probability of success, and Q is the probability of failure. Since the events are mutually exclusive in the entire sample space for a single trial, we have 1 minus P equals Q, right? P plus Q equals 1. And we can use this formula to determine the probability of a certain number of successes, R, and failures in a set of K trials. Since X bar is an estimate of mu, right? X bar is just our sample mean. Mu is our population mean. We find that X bar, our sample mean, is equal to K times P. So our number of trials times the probability of success will give us the mean number of successes. P, so our probability of success, is therefore X bar divided by K. Mean and variance are also related. So the mean, mu or X bar, again, is Kp. Our sigma squared represents our population variance. This hat, this little like caret thing above it, is sigma squared hat, and it means that it's an estimate. So our variance is equal to Kp times 1 minus P, or Kpq is the same thing. And because Kp is equal to mu, our variance is also equal to mu times Q. So our average times the probability of a failure. And we use this estimate of population variance and compare that to our sample variance, which we can actually calculate with our samples. These equations are really important for you to know how each term is related. So definitely memorize these. Okay, so on page 61, there's a worked example. We're going to go through it in Excel, but at first I'm going to go through it with these slides to just kind of explain how you would approach these problems. So for this example, there are 30 samples. So n equals 30. Our sample size is 30 of 5 insects. So k equals 5. And we examine these to see, I'm sorry? Did someone say something? Okay. So each sample has 5 insects that we're examining for infection by mites. So a lot of people get really confused between this sample versus trials, like number of trials K. So for this, really what you would be doing is imagine picking up 5 bugs in your hand, and you're looking at each of those bugs to see if they're infected. Your sample is the 5 bugs. You're sampling them all at once. Your trials are 5 though, because you have 5 insects that you're looking at a time. And for each of those insects, you either have a success or a failure. In this case, we're calling a success an infected insect, and we're calling a failure a non-infected insect. So for each of those 5 bugs, we're saying, is it infected or not? If it's infected, that's a success. If it's not infected, it's a failure. So this is the information that we're given. The first approach to solving these problems is using observed and expected frequencies. And this is specifically when I provide you with data to use in a data table. Oh, back up. So in the event that you need to solve this way, I will give you a data table like this, or at the very least, I'll give you these 2 columns of data for you to solve everything from. So the first step is to calculate the mean number of insected insects per sample. So the mean number of successes per sample. And we find X bar using the data in the table for columns 1 and 2. This is where the weighted mean comes back into play. Remember, we talked about the weighted mean last week, and I kept alluding to that it would be more important this week, and this is where. So our total, right here, I have this like summary table. Our total is our samples. So we have 30 samples. We use the equation for the weighted mean. So our mean is equal to this xi fi from 0 to 5. So 0 infected insects to 5 infected insects. So we're essentially doing that sum product, remember? So we're doing this times this, plus this times this, plus this times this, so on and so forth. That's sum product function that I was showing you last week. And that's here. We then divide that by our total sample size. So 88 would be the numerator. The number of infected insects is what that means. The numerator represents the number of successes, the total number of successes per trials. We then divide that by the number of samples we've taken, which is 30. So we calculate our weighted mean, which is over here, that's our X bar. Using those equations from before, we know that X bar equals Kp. So we can now solve for P. So our probability of success is equal to the mean number of infected insects divided by the number of trials, which is 5, which we get here. So our probability of success, our probability of having an infected insect in our trials is 0.5866. We then calculate the expected frequencies using the p-value or the probability value that we just calculated, using the binomial probability formula for successes for values x equals 0 through x equals 5, or r equals 0 to r equals 5. X and r in this case are interchangeable. You don't actually have to use this equation for our lab. We'll be using a binomial function in Excel, but for your lecture, you might have to do this by hand. So here's that written out as well. So we have 5 factorial k factorial divided by r factorial times k minus r factorial. Here, this 1 is that probability of success raised to the number of successes, which in this case, we're starting with 0. So any number raised to the 0 power is 1. And then we have 1 minus p, which is q, right? That's our probability of failure, raised to the k minus r power, which is our number of failures. Solving that, we get 0.0120, so on and so forth. We have to do that for each of these values though. For x or r, again, x equals r, they're the same thing. They're just written different ways sometimes. Or xi, I should say, xi and r are the same thing. So you have to do that for each of these values. which I have up here. So x equals r. To fill in the rest of this column. Next, you need to multiply the expected proportion / frequency / percentage we just calculated by the total number of samples to get the absolute frequency. So for this first one, we do the probability of a success times the number of samples to get the expected frequency of successes. So the way to think about this is our proportion is our probability or our percentage of times that we expect to have a success, which in this case, a success represents an infected insect, right? So we expect to have 6.9% successes in this example, or 6.9% where 5 out of 5 insects are infected. That's what this is. So this is our number of successes. So 5 out of 5 insects are infected. We expect that to happen 6.9% of the time. If we want to translate that back into number of counts or frequencies, we need to multiply that percentage, that probability, that proportion by our sample size. So out of 30 samples, we would expect 2.08 to have 5 successes, to have 5 infected insects. And we repeat that for each of these. So for 4 infected insects out of a sample of 5, we would expect that to occur 24.4% of the time. 0.244 is the probability or proportion of having 4 infected insects out of 5. Multiplying that by 30, we get 7.3. We would expect that to happen 7.3 times out of 30. Finally, we have this deviations column where we subtract the observed frequency from the absolute expected frequency to get the difference. And we repeat this for all values again. So in this example, we actually had 5 samples where 5 insects were infected. We do 5 minus this, so the observed frequency minus the expected frequency to get the difference between the two of them. We found that we had 2.915 more samples with 5 infected insects than we would have expected if this data fit a binomial distribution. And finally, we have this plus or minus column, which I'm not going to ask you to do, but I've included here just to see how the data relates essentially to a binomial distribution. So the positive deviations at the tail end, so here and here, mean that the data is non-random and does not fit a binomial distribution. If it did, we would expect the observed minus expected differences to be 0 or close to 0, because that would mean that there is a very small difference between our observed frequency and our expected frequencies, right? That means that they're almost identical. So we can kind of ask ourselves now which assumptions were probably not met. So looking at this, the probability of success may not have been constant and the sampling procedure may not have been random. Those are 2 possibilities. There's a second approach to solving binomial problems, and that's using the mean and the variance. And you're going to do this when you don't have a data table, when I don't give you a data table, but I just give you some values to calculate using. So remember that X bar is equal to KP. So in homework problems, quiz problems, exam problems, I'll probably give you some values, probably the mean and the probability of success or something like that. But here we already have them. We already calculated them as well from step 1. So we can use our probability of success to estimate our expected variance. Using that equation from before, remember, Kp times 1 minus P is the same thing as X bar times Q. And those are all equal to our estimated variance. So using that equation, we find that our estimated variance, our expected variance is 1.213. We can then actually use the original equation for calculating sample variance to calculate our actual sample variance. We then find that our sample variance is greater than our expected variance. So there's more variance in this data than we would expect, which means there are too many samples in the tails of the distribution. So we come to the same conclusion using this method as the previous method. Okay, so we will go ahead and do the binomial example in Excel. As usual, I have this new functions tab for you that I recommend you look over. So we've got sum product, which you should be familiar with because we used it last week. This factorial one, which calculates the factorial of the number in the parentheses. You don't actually have to use this. This would be in the event of actually typing out the factorial equation in Excel, which I'm not going to have you do because it introduces a lot of room for error and it's not necessary. This if function also can print different things using a logical test. These are both kind of just remnants from the lab manual and how they have you do these chapters. I'm not going to ask you to use them, but I wanted to include them in case anyone was curious. We're going to really focus on using this binom.dist and Poisson.distribution functions. So what goes into the binomial distribution function is our xi or r, right? They're the same thing. So it's the number of successes, then our total number of trials per sample, our probability of success, and then a 0 or a 1 as this final term. A 0 gives you the probability for that specific xi or r, that specific number of successes. The 1 gives you the cumulative probability. So that's for xi and all previous numbers before. So right, if xi in this example is 5 and I did a 0, it would just give me the probability of 5 successes in 5 trials. If I put a 1 at the end instead of a 0, it would give me the probability of 5, 4, 3, 2, 1, or 0 successes, all summed together. The Poisson one, which we'll get to later if we have time. If not, I will just be recording it and posting that later. Works in a very similar way. So it's the number of the observed number of successes. It's not quite successes though when we do Poisson. The mean and then a 0 or a 1, which works the same way for cumulative or non-cumulative distributions. Here I've got the functions for you for solving the binomial distribution problems too. Okay. So for the first example, we have approach 1. So you're given a table and you use the table to calculate the necessary values. So the first thing I like to do is fill in as much information as I can. So yeah, fill in as much information as possible. In this example, I already know that we have 30 samples, but we could also sum up our observed frequency to find that too. And this is the first thing I recommend you do, is to find the sum of your observed frequencies, because that tells you how many samples you have. The next thing we can do is calculate the total number of infected insects. And there's a couple ways to go about doing this. You can first use this XI-FI column, which you won't find on the in the lab manual, but we've included it because we think it helps helps make all of this a little bit clearer. So that would be this times this value. So our number of infected and the observed frequency, how many times we found a sample with 5 infected insects. So that actually gives us, this 25 represents the number of infected insects, the number of successes that we've seen. And we can do that all the way down. I'll just move this total across here. So we have 88. That means out of our 30 trials, we found 88 infected insects, 88 successes. We also have this total number of insects. So we had 30 samples of 5 insects, right? K equals 5, which means that our total number of insects is 30 times 5, right? Okay. Next, we can calculate our probability of success using our equations, right? Or actually, let's calculate X bar first. So we'll calculate X bar using that weighted mean problem, or that weighted mean equation. So you can do either XI-FI, right? This is the sum of XI-FI right here, divided by N, our number of samples. Or you can use that sum product function that I showed you the other day. Sum product of this column and this column divided by our total number of samples. So now that we have X bar and K, we can also calculate P and Q. Remember, because X bar is equal to KP, that means P is equal to X bar divided by K. So that's our probability of a success.
How did you find the X bar again?
X bar is given by that weighted mean equation. So that's the, hold on, I don't know if this will work. Okay. So that's given by this equation. So the equation for a weighted mean. And like I said, there's a couple ways you can do that. What's here is this divided by this, because this number right here, this 88, is equal to the sum of XI-FI, right? Because this column is XI-FI. It's literally XI times FI. All the way down. And then this bottom row is just sums across the board. So that is the sum of xi times fi. And then I'm dividing that by our sample size, which is 30. Does that make sense?
Yes, thank you.
Okay. I'll leave that there. Okay, so now that we've got this, and then we calculated P using X bar divided by K to get our probability of a success occurring, and Q is just equal to 1 minus the probability of a success. So our probability of a failure. Now we can actually calculate probabilities using a binomial distribution. So up here, I've got this awful factorial equation that I don't expect you to ever type or use or memorize how to do. But I just wanted to show you that it could be done and that you should be very thankful for the binomial dot distribution function, because if we didn't have that, you would have to type this for everything. But luckily, we do have this binomial dot distribution function, and we can use that instead. And we use it doing this binom dot dist, so that's the function. And once you start typing that, Excel gives you kind of like a cheat sheet of what you need to put inside. So number S, that's the number of successes, and that is our xi. Followed by our number of trials, which in this case is 5, that's our k. And I'm going to go ahead and anchor that so that when I drag this downward, that doesn't move. Next is our probability S, our probability of a success, which is P, which again, I'm going to anchor so that it doesn't move when I drag down to fill out the rest of this table. And then finally, true or false or 0 or 1. True means a cumulative distribution function. False means a probability mass function. So just for this value, and I'm going to do that. So a 0. And we get the same number that we had before using the calculations with the factorials. But obviously it is much easier, much faster, much safer and less likely to make errors doing it this way. So I'm going to click and drag to calculate the rest of those. And here we should find that the sum is 1, right? Because this is all possibilities in the sampling space. Out of 5 samples, we either got 0, 1, 2, 3, 4, or 5 infected bugs out of 5 infected bugs. To calculate our expected frequency, we take this value and multiply it by our sample size to find out of 30 samples, right? 30 is our sample size, how many of those would we have expected to have this number of successes, 0 through 5. Times our sample size. You can click that one, or you can type it, the actual number 30, that's fine too. Oh. But I'm going to anchor this cell so it doesn't move. And we should find again that our sums sum to 30. If this doesn't equal your sample size, you gotta double check what's happened up here because there's something going wrong. And then finally, we have our deviations column. So that's our number observed, our observed frequency. How many did we actually see minus how many should we have seen if this was a binomial distribution? So Justin's asking, how do you know if you use a 0 or a 1 in the binomial function? That really depends on the problem, and I'll show you that in 1 second when we get over to these probabilities. So we can drag this down, and this just really shows us like, if all of these values are close to 0, it means our observed frequency is pretty close to our expected frequency, which is good, and that the data roughly fits a binomial distribution or fits it better. We also have this observed variance and expected variance, which honestly on quizzes and things like that, I don't think I'm going to ask you any questions about it because it's kind of, it's not super relevant, and it's kind of like, I don't know, it kind of changes person to person. Like, you can argue different things, but I'll just show you how you would do that. Anyways, your expected variance would be using that one calculation from before, right? That was our mean times our probability of a failure. So our mean times our probability of a failure. Our observed variance is a little tricky. You have to transform the data into like our raw data format. And what I mean by that is here we've got number of infected and observed frequency. So for 5 samples out of 30, we saw 5 infected bugs. We saw 6 samples with 4 infected bugs. We need to transform this into raw data. So what I mean by that is we saw 5 infected bugs 5 times. So 1, 2, 3, 4, 5. 4 infected bugs 6 times. 3 infected bugs 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. 2 infected bugs 6 times. 1, 2, 3, 4, 5, 6. 3 infected bugs with 1 bug, or sorry, 3 samples with 1 infected bug. 1, 2, 3. And 2 samples with 0. And this should give me numbers 1, 30, right? 1 through 30. So that I can make sure that I'm accounting for all 30 samples. So if you were actually out in the field collecting data, this is what your data set would look like. So that's what I mean when I refer to this as like our raw data format. Using this, now we can actually use the var.s function that we've been using to calculate the variance. So this is our actual variance for our sample, whereas this is how much variance we would have expected under a binomial distribution. And we see that they're a little bit different from each other. Okay. But again, like I said, I'm not going to ask you any questions about that because you can argue different things. It's not a really clear right or wrong answer. Okay, so the questions I am going to ask you on quizzes and exams are going to be more probability based. So here I'm asking you, what's the probability of having 4 infected insects in a sample? Well, you could use the binom.dist function again for 4 samples, but we've already calculated over here in the table. For 4 infected insects, we would expect to see 0.244 roughly it as our proportion. That's the proportion or the probability of having 4 infected insects in our samples. 4 or more insects would be 4 or 5. The probability of 4 or 5 insects in a sample being infected. All right, so the probability of 4 bugs plus the probability of 5 bugs. Here we have the probability of at least one insect being infected out of a sample. So that would be the sum of 1 to 5. And then finally, we have the probability of less than 3 insects. So there's a couple of ways to go about doing this one. So you can do what I've been doing before, just the sum function, less than 3 insects being infected out of a sample of 5, right? That would just be 2, 1, or 0. Or this would be a time where you could use a 1 instead of a 0 to find a cumulative probability. If you did that, you would use the binom.dist function for number of successes as 2. Number of trials is still 5, or k. Our probability of a success is over here, and we do a 1. Because what that 1 tells Excel to do is the probability of 2, 1, or 0, which is the same thing that we calculated using the sum function. But if I didn't have this table completely filled out with all of these probabilities, I wouldn't be able to use that. I'd have to have done this version. Which you'll see for the binomial example 2. So this is approach 2. So in this approach, you're not given a table, or I won't give you a table. Instead, I'll just give you some variables, and using these equations, you'll have to calculate everything else. So now you're studying the same population of infected insects, but this time you don't have the data table you had before. Instead, you know that you're sampling 6 insects at a time, so our K value is different. Our trials per sample has changed. It is now 6. And based on our previous sampling, the average number of infected insects per sample is 2.5. So I've told you in this example that the X bar, the mean, the average number of infected insects per sample is 2.5. So we can now fill out the rest of this and then calculate the probabilities. So the probability of success, remember, from here is X bar divided by K. Our probability of a failure then is 1 minus the probability of a success. And finally, our variance, our estimated variance, population variance, is equal to X bar times our probability of a failure, Q. So now what's the probability of 4 infected insects? We have to use the binom.dist function. For 4 is our number of successes. 6 is our number of trials, or you can click this cell either way. Our probability of a success is P. And this question is not cumulative. We're asking just for the probability of 4, not for the 4 plus 3 plus 3 plus 2 plus 1 plus 0. 4 or more insects. There are a couple ways we could do this. We could do the binom.dist for, well, I guess actually we could do this since we already calculated 4 plus binom.dist for 5. 5, 6, probability of success, and 0 plus binom.dist for 6. So 6 bugs out of 6 trials. Probability cumulative is 0. Probability of at least 1 insect. Well, okay, so again, there's a couple of ways we can do that. I also have this table over here where if you wanted to, you could do all of the binomial distribution calculations first so that you can sum them like we were doing before. I'm going to anchor that cell. I'm going to drag. It's not going to be different, but I can just change these numbers here. There. So now we have, and I'm going to use this as well just to double check that that's all right, right? The number here should be 1, which it is. So instead of typing out the binomial equation like this, you could calculate everything first, and it'll make everything for answering the questions actually a little bit easier. So the probability of at least one insect would be 1 and up, right? Probability of less than 3 insects, again, could be this. Or you could do binom.dist (2, 6), the probability of a success, 1. And I think I accidentally actually selected 3 in this example too. So for question 1 on page 69, we're asked, when given a crab and a clam together, it has been observed that an octopus will eat the crab first with a probability of 0.8. If we run the experiment 4 times, what are some probabilities, right? So first off, it's important to define a success. In this case, our success is eating a crab first. Out of how many trials, right? 4 trials. There are 4 trials that we're going to see. Does the octopus eat the crab or the clam first? And the probability of a success, which we've defined as crab first, is 0.8. So this is all information that we've been told, except for this, I suppose. So now we can use the binomial distribution function to calculate some probabilities. So what is the probability that the octopus will eat the crab first in 2 of the trials? So we've got binom.dist. Number of successes is 2, crab first in 2 of the trials out of 4 trials. The probability of a success is right here, P, and it is not cumulative. Now we're asking, what is the probability that the octopus will eat the crab first in at least 2 of the trials? At least 2 means 2, 3, or 4 out of 4 trials. So the binom.dist of, I'll just click this one, actually, hold on. Equal to the probability of 2 plus binom.dist, the number of 3 out of 4 trials. The probability of success is still 0.8, not cumulative. Plus binom.dist, for 4 out of 4 trials, same probability of success, 0. So that's our probability of a crab, or sorry, not a crab, an octopus eating a crab first in 2, 3, or 4 out of 4 trials. And finally, what is the probability that it will eat the crab first in all 4 trials? So binom.dist 4, 4. So 4 out of 4 trials, and it is not cumulative. For question 3, so we have assume the probability of having a female child is 1/2, which for the most part it is, right? So go ahead, we can figure out all of these. So for number 3A, how many families out of 1,000 families with 4 children would each would you have, sorry, for a total of 1,000 family with 4 children each, would you expect to have at least 1 daughter? So we're going to define the success as having a female child, having a daughter. K is a little tricky here, right? So we have 1,000 families with 4 children each. K is not 1,000. That's our sample size. K in this case is 4, because there are 4 children born per family. Our probability of success is 1/2, and our sample size, N, is 1,000. So how many families out of a total of 1,000 would you expect to have at least 1 daughter? So this is kind of a multi-part question. So I'm going to actually solve this a little bit off to the side. So we've got, first we need to find the probability of having at least 1 daughter. So that'd be 1 out of 4 trials. The probability is 0.5, 0, plus the probability of having 2 females out of 4, plus, keep doing that, plus the probability of having 3 out of 4 daughters, plus the probability of having 4 out of 4 daughters. So that's the probability, but this question asks us, how many families out of 1,000 would you expect? So we actually need to multiply this by 1,000 so that we get a whole count number, because right now it's 93.7% essentially, right? So this is 1,000, or our sample size I could have done as well, times the probability. And we see that we would expect 937.5 to have at least 1 female child. For B, we're asking how many families would have no daughters. So that's just the complement of that, right? To bring it back to probabilities, the opposite of that. If 937.5 families would be expected to have at least 1 female child, that means the remaining number we would expect to have no female child or have only sons. For 69, or page 69, question 4. In a large population of starfish, orange individuals are 3 times more numerous than purple individuals. That means that we have a 3-to-1 ratio of starfish, of orange to purple starfish, which means that let's say that we had a group of 100 starfish, a 3-to-1 ratio really just breaks down to 75% orange and 25% purple. So let's say orange is our success. It means our probability of a success is 0.75. That complies with our 3-to-1 ratio. So what is the probability of obtaining a sample of 18 starfish in which 8 are orange and 10 are purple? So K, our number of trials in this case is 18. And using our binomial.dist function, we're looking at, what is it? 8 are a success. So 8 successes or 18 trials. The probability of success 0.75, not cumulative. For B, we're saying what's the probability of getting all purple starfish in a sample of 4? Well, we have a couple of options here. We can keep orange as our success, or we can switch it to purple. Since the question is asking about purple, it does seem to make a little more sense to switch it. In this case, we have 4 trials. It's a little tricky because it says a sample of 4. But the way that you need to think about this is in a sample or in a trial, can you have a single success or a failure? If the answer is no, then it's our sample size. If it is yes, then it is a trial. So in 4 picks of a starfish, can it be a purple versus orange? Yes. Again, our probability of success is now reversed, so it's 0.25. So what's the probability using the binomial.dist function? For all purple, so 4 out of 4 trials, for C, what's the probability of getting 14 orange starfish in a sample of 25? So we're switching back to orange for our success. There's going to be 25 trials. Our probability of success is 0.75 again. And we're asking for 14 out of 25. And there we go. That's our probability of success. Question 6. An oil prospector has enough money to drill 4 wells. During his long career, he has found that he strikes oil in a quarter of the wells he drills. So oil, strikes oil, I should say, is a success. He's drilling into 4 wells, so that's 4 trials, and our probability of success is 0.25. For A, what is the probability that he will strike oil in at least 3 of the 4 wells? So this would be binomial.dist for 3 out of 4 wells, not cumulative, plus binomial.dist 4 out of 4 wells, the probability up here, not cumulative. For B, what is the probability that he will not strike oil? So not at all. So completely fail would be binomial.dist strikes oil on 0 out of 4 wells. And finally, in how many wells should he expect to strike oil? Well, you don't really need to use the binom.dist function to solve that one, right? So it's just the probability of a success times the number of trials, right? A quarter of the times, 1 out of 4. You should expect to find oil 1 out of 4 times. And then finally, for page 70, question 8, the following data represent the number of males in schools of 6 damselfishes. The investigator was interested in knowing whether schools assemble at random or whether there are greater or fewer males in these schools than would be expected due to chance alone. The latter finding is important in the theory of sexual selection, as mating is believed to occur in these temporary schools. So here is the data split into XI-FI, so the number of males, and the observed frequency. So these are schools of 6 damselfish. So 6 is our number of trials. And we're sampling these schools of 6 fishes several times. And let's see how many times. By summing up our observed frequency, we get our total number of samples. So we sampled 100 schools of fish, which means we sampled 600 schools, or 600 fish total. Using XI-FI or sum product, right? We can get, let's do both actually. So we'll do sum product first. We can get the number of successes, or the number of males in the number of successes total, which in this case is the total number of males. Using sum product, we would select this column, comma, this column. We find that there were 150 males total. We can also use this XI-FI column to calculate that as well. Kind of breaks down that sum product step a little bit more. And then I'll just drag this sum function all the way across. And we get the same thing, 150 successes total. I'd like to then go ahead and calculate X bar, which is equal to the XI-FI, the sum of XI-FI, that's 150, divided by the total number of samples, which in this case is schools, the total number of schools sampled. So 1.5. The chance of a success, or the average number of male fish per school, is 1.5. We can then calculate the probability of success as X bar divided by the number of trials. And our Q, our probability of failure, is 1 minus P. Now we can fill out the rest of this table and answer the questions. So here we've got the probability of 0 males out of 6 trials. Remember, you can do it this way, or you can just type the number 6, either way. The probability. This way is nice if you end up editing this in some way. That's not really relevant for this course, but in general in life, I suppose, if you're using Excel, it's nice to refer to cells so you don't have to manually change them if any data changes. There we go. So those are the individual probabilities of each number of observations of males per group of 6 damselfish. Our expected frequency is our expected proportion times our number of samples, which again, I'm going to anchor. And finally, our deviation is the observed frequency minus the expected frequency. Oops. So now we can answer the question. So what is the probability that you would find more than 3 males in a school of damselfish? More than 3. So 3 or more. So 3 through 6 in a group of 6. We're summing those probabilities. Oh, sorry, we're summing more than 3, so we're not including 3. So 4, 5, or 6. For B, what is the probability that you would find 5 females in a school of damselfish? This is kind of flipping it a little bit, right? If we have 5 females in a school of 6 damselfish, that means there's only 1 male. So this is the same thing as saying, what's the probability of finding 1 male in a group of 6 damselfish? For C, how many schools of damselfish would you expect to have 2 males? So this is how many schools, not the probability, but how many actual number of schools. This is actually, we already calculated for number 2. So expect to have 2 males. Here's the probability. Here's the probability times 100, the total number of samples that we collected. This is how many schools we would have expected to find that have 2 males. And for D, how many male fish are in a damselfish school on average? And that's just equal to our X bar. For Poisson distribution, this is for a random distribution. So while binomial is essentially a normal distribution but discrete, Poisson expects that there is a random distribution of either individuals per unit of area or a frequency of an event for a fixed period of time. So individuals per unit area, that would be like the number of birds in a kilometer squared. For frequency of events for a fixed period of time, that would be like number of birds flying overhead in an hour. The Poisson distribution assumes that the number of individuals per unit area or the frequency of events per fixed period of time are random. So not clustered together or uniform, happening, like one bird flies overhead every 1 minute and 36 seconds, right? That wouldn't be random, that would be uniform. Same if you found birds in a clumped distribution, right? Maybe you find like 10 birds clumped together roughly every like 20 meters. That's not a random distribution, that's clumped. The assumptions of the Poisson distribution are that individuals or events occur randomly in respect to each other. That individuals or events are relatively rare. The less rare they are, the less random they are. It's not Poisson anymore. And that the probability of an individual or event occurring is proportional to the sampling unit, which makes sense. If you have a big quadrat, you're more likely to sample rare individuals. if you wait for a longer period of time, you're more likely to have a random event occur. Poisson, like binomial, also uses count data. And we assume, this is very important for the Poisson distribution, that the mean is equal to the variance. The equation for Poisson distribution is that P of x, or the probability of x, is equal to the mean raised to the number of successes, or the number of times that event occurs, really, times Euler's number, this E, which is a constant, raised to the mean, divided by x factorial. So the number of individuals or events per sampling unit factorial. Sometimes instead of using x bar, people will use lambda. So both are here. And they mean the same thing. They just represent the sample mean. And it's used very, very similarly to binomial. And again, I'm not going to ask you to use this equation in class or on your assignments or quizzes or exams or anything like that, but it is important, of course, to know where these numbers are coming from. So using this equation, again, is very similar to binomial. So for the mean number of birds flying overhead in a minute is 4.3, and flight is random in relation to each other. Therefore, the probability of no birds in 1 minute is P of 0 is equal to the mean raised to the number of birds flying overhead times Euler's number raised to the mean divided by 0 birds factorial. And just so everyone knows, 0 factorial is 1. It's kind of a weird math thing, but it is. So the probability we find is then equal to 0.0136. One big difference between Poisson and binomial is that the numbers of a Poisson distribution go on infinitely, but the probabilities rapidly approach 0. So what I mean by this go on infinitely thing, is the mean number of birds flying overhead in a single minute, right, the average is 4.3. I could ask, what's the probability that 4,530 birds fly overhead in the next minute? And we could calculate the probability for that, but it's very, very low, right? The idea of that many birds flying overhead in a single minute is almost absurd. So the probability for that exists, the numbers go on infinitely, but the probability of those higher numbers, those extreme values, rapidly approaches 0. Even here, with this example, we find that the probability of 25 birds flying overhead in a minute, with the mean at 4.3, much lower, is very low. The probability of 25 birds flying overhead is 6.0062 e to the negative 12. So it's practically 0. The highest probability will be at the mean, which is pretty intuitive, but I just wanted to double state it here. So again, the highest probability is at the mean, and the numbers of the Poisson distribution go on infinitely, but the probabilities rapidly approach 0. Because of this, we often solve for this probability of greater than x, which is the probability of seeing a number of observations greater than x. This figure here shows us what a Poisson distribution curve looks like. If the mean, lambda, is 1, then at 1 we have our greatest probability, and they rapidly decrease to practically 0. For our mean of 4, our probability is greatest at 4, so it increases and then rapidly decreases as we're asking for higher values, so on and so forth. Instead of using well, no, I guess that's not exactly what I'm trying to say. So when we're solving for this probability of greater than x, we subtract the cumulative probability from 1. So let's say that we have a problem and I'm asking, what's the probability that more than 2 of whatever event will occur? We would actually do 1 minus the probability of, I guess, 2, 1, or 0 to get greater than 2. Yes, yeah, so the probability of less than or equal to 2. So the probability for 2 or 0, 1, and 2, we subtract that to get all remaining probabilities, the probability of something happening more than 2 times. I said before, this works very, very similarly to Poisson. So the first thing that we can do is calculate the sum of our observed frequencies to get our total number of samples. So this is from page 76. Sorry, let me back up a second. This is from page 76, where you have a total of 64 meter square quadrats that are placed at random to sample the number of benthic black fly larvae on a stream bed. The observed frequency of number of quadrats containing from 0 to 8 individuals were determined. So that's what these values are. This total here represents the total number of quadrats, or the total number of samples we took. We can then calculate this total number of individuals sampled, or the total number of individual samples. So not successes in this case, just the total number of individuals in general. And we can do either the sum product function or calculate the xi/fi separately here. So use sum product first, which is just this column, comma, this column, close parenthesis. Now, what is kind of strange here is that you can't include this bottom row in the sum product function, because this greater than 8 doesn't work as a like a number, right? You can't multiply something by that. In this case, it works out nicely because it's actually 0. So let's say this was a 9, for example. 9 times 0 would still just be 0. So it would be adding 0 to these products. So it's actually works out well. And again, we can calculate that using the xi/fi column as well, doing it more step by step. So you'd get the quadrat times the individuals per quadrat, and the frequency observed. So there were 2 times where a quadrat had no fly larvae. Right, and if I did try to drag that all the way down, we'd get an error down here. So this number represents the number of times we saw a quadrat with more than 8 individuals. In this case, that happened 0 times. And then if we sum these values, we get the same thing we got here. So this represents the total number of individuals that were sampled. So that's a very, very key difference between binomial and Poisson. The xi/fi means something different. It's not the total number of successes, it's the total number of individuals sampled in general. When we calculate X bar, we do it the same way though. So we do, it's still the weighted mean. So it's our total number of individuals per quadrat. But it means something a little bit different this time, right? It doesn't mean how many successes per sample. It's how many individuals per area, per unit area, or per time period. In this case, there were roughly 3.68 individual fly larvae per quadrat. Now we can calculate our expected proportions using the Poisson dot dis function. Here we need x, so the number that we're asking for 0, our mean, and cumulative, which in this case is 0. And I'm going to anchor this C20. So another weird thing, right? If I try to drag all the way down, I get this value error. Again, because of this. So instead, what we're going to do here is we're going to say 1 minus the probability of 8 or fewer. So this is the perfect time to use this one. This Poisson function is going to calculate the probability of 8, 7, 6, 5, 4, 3, 2, 1, and 0 fly larvae per quadrat. That's what the 1 does. It sums everything from 8 downward. And that gives us our remaining probability, the 1 minus. And again, our total should always equal 1 for this. Our expected frequency is the same thing as binomial. It's this times our sample size, or the number of quadrats. I'm going to, again, anchor this and click and drag down. And this should equal our sample size, which it does. So we would have expected, if everything was a binomial distribution, or not binomial, I'm sorry, a Poisson distribution, and everything was randomly distributed, we would expect to find 13 quadrats with 3 individuals. And finally, we have our observed minus expected column. So our observed frequency minus our expected frequency to get a deviation, to see how much did our actual data vary compared to what we would expect. Now we can answer our questions. So for A, what is the probability you would expect to get more than 8 fly larvae in a quadrat? That is what we calculated here, more than 8 flies per quadrat. This is the expected probability. For B, what is the probability of getting at least 1 fly larvae in 1 quadrat? That would be the sum of all probabilities 1 and greater. For C, how many quadrats would you expect to have 5 fly larvae in them? And we're asking how many quadrats, not the probability. So we're actually for the actual expected frequency. Okay, here is where I recommend you pause the video and you work through these two examples on your own. Okay. So solving these problems on page 80. For the first one, we're asking about the dispersion pattern of gopher holes in a large pasture and wondering whether gopher holes are randomly distributed in the pasture or whether they are clumped or aggregated in certain areas. We count the number of gopher holes in 196 1 square meter quadrats. And this is the data from that. So 197, that's what we should expect this sum right here to equal. And it does. So that's our total number of quadrats. This XI, should give us our total number of individuals, right? Or we can use, again, the sum product. Again, it really works out because we didn't have any quadrats with more than 9 individuals. So this would be 0 times 9. And this should really say greater than 8, actually, so that we're still including the number 9. So it'd be 0 times 9 would be 0, so we're not missing anything here. And again, we can do that kind of in 2 steps using this XI column. But it doesn't work here, but we'd have 0 times 9, so 0. We sum this, should get the same thing, 613, and we do. Our mean then is our total number of individuals per quadrat. Our expected proportion is what we calculate using the Poisson function. So xi, comma, the mean, comma, 0. And I'm going to come up into the equation bar and anchor the mean. Click and drag that all the way down. And I'm just going to grab this sum function across. But it didn't work here, again, because of this. So we have to actually calculate this one. This is equal to 1 minus the probability of 8 or fewer, which is the 1, the cumulative 1. We can check this does equal 1, so that's good. The expected frequency is this expected proportion times our sample size, which is the number of quadrats that we had. So click that and drag down, and we should have, oh, I forgot to anchor my value. So that's why we're getting that error. Anchor the number of quadrats, try that again, and it all works out fine. Finally, the observed minus expected. So observed minus expected. So how many quadrats will you expect to find more than 9 gopher holes in? So that's equal to this. That's our actual expected frequency. That's the number of quadrats. So almost 1 quadrat. What is the probability of finding 4 or less gopher holes in a quadrat? you can do the sum of the sum of 4 or fewer for the probability. For question 2, we're trying to determine whether individuals in a species of spiders are randomly spaced in a field. So we count the number of male spiders in 100 different 1 meter squared quadrats in the field and get the following data. So we did 100 quadrats, so this number right here should equal 100. And it does. Number of individuals, again, we can do sum product between these two. We get 66 total number of spiders. And again, it works out really well, almost as if somebody planned that, that this would add to 0. We can do xi fi over here. I get this value error, but it would also be 0. And I'm going to just grab that sum all the way across, and we get the same thing, 66. X bar we calculate with our total number of individuals per quadrat. Expected proportions using the Poisson distribution function for our xi, our mean, and 0. It's not cumulative. Select and drag. Oh, I forgot to anchor. Very important. And then here, remember, we have to do 1 minus the probability of 3, the mean, and then a 1 there instead for 3, 2, 1, or 0. And we get our sum is 1, which is great. Our expected frequency is then our expected proportion times our sample size, the number of quadrats, which I'm going to remember to anchor this time. I click that and drag down. And again, our expected frequency total equals the same as our observed frequency total. And last, we have our observed frequency minus our expected frequency. And click and drag. And our table is filled in and we can answer these questions. So how many spiders on average does the ecologist find in each quadrat? That is just our X bar. And how many quadrats would you expect to find no spiders? And that is our expected frequency for 0 spiders per quadrat. And that's that.